Okay, polar coordinates, you guys, we're going to convert. Goal number 1, we're going to convert between polar and rectangular coordinates. Goal number 2, to graph in polar coordinates. So what are polar coordinates? It's another system for locating a point in a plane, or points, plural, in a plane, using a radius and an angle. So if you think about it, the coordinate system you're used to is called rectangular coordinates. We go left or right or up and down from the origin to locate a point, right? Here, it's going to be a little different. Let me show you. Let's suppose you have a point in the plane, and I'd like you to draw a little horizontal line. But it's not a complete line. It's more of a ray. It has a beginning point, which would coincide with the origin, I suppose. If you want to relate this to something you're familiar with, it would be like the positive x-axis. This ray that I've drawn would coincide with the positive x-axis. And this point right here, which we call the pole, would correspond with the origin. So then we have this point. You're used to representing the coordinates as x, y. So in regular rectangular coordinates, you would go from the pole right x units, whatever x is, and up y units to get to it. That's what you're used to, right? And it's called rectangular coordinates. I think it's pretty obvious because if you went right x units and up y units, you'd be at the corner of this rectangle, wouldn't you? So it's called rectangular coordinates. That's what you're used to. But what's another way to locate that point? Well, you could go directly there from the pole, from the origin, essentially, and measure that distance, which we would call r, or a pirate would say r. Yeah, I know, I use that joke too much. So that distance is r. And then you guys are very familiar with a related angle. The angle formed between usually we call it the x-axis. Here we'll call it the polar axis, I suppose. So polar axis, same as the positive x-axis. And it would be the usual theta, wouldn't it? The same theta as the direction angle when we're talking complex numbers or vectors. And so we would represent in polar coordinates this point x, y as the point r, comma, theta. So what you need to do, or the way you need to change your thinking when you're in polar coordinates for point-wise, is you have to think radially, like spokes on a wheel, and angularly. I don't know if that's a word. Keep making up words this week. Angularly. Instead of left, right, up, down, right? But it's not complicated. I'll show you. Look. So notice how my graph paper has changed. It looks like a wheel, right, with spokes on a wheel. And concentric circles, right? So let's go ahead and plot the point 2 comma pi thirds. How to think about it? Well, okay, what's the pole, you guys? The pole, here's the pole, which is, well, you can't see that, so let me do it in red. The pole would be here, right, at the center of all these concentric circles. And the polar axis would be here on my graph paper. So before I plot this point, let's talk about a few angles. 0 radians, you're looking straight right from the pole, right? It would coincide with 0 degrees. If you look straight up, that would be pi over 2 radians, which is the same as 90 degrees. We'll switch between degrees and radian measure here. Straight to the left, you're talking pi or 180 degrees. Pi. If you go 3/4 of the way around from the positive x-axis or the polar axis, you're at 3 pi over 2. Familiar stuff, right? Which is 270 degrees. So the way this particular type of graph paper is broken up, well, what angle must this first spoke be at? The way I've broken it up here, it looks like it's probably, 30 degrees, which would be what? pi 6, right? Then we have one that splits the upper right-hand quadrant, the first quadrant in half, so pi fourths. And then this guy, pi thirds. Okay, now we're on our way. Let me erase some of this stuff we don't need. Okay, so 2 pi thirds. A couple different ways you can graph it. Okay, you can think of the angle first and sweep out an angle of, well, here's theta, right? Pi thirds. So you can sweep out an angle of pi thirds, and then how far do you go out? 2. Now, the way I like to think of it, though, I like to go out the distance first. I like to go out the distance of 2. So from the origin, I'm here, go out 1, 2, I'm here, and then sweep out the angle along this piece of this arc of the concentric circle, of one of the concentric circles at radius 2. And so that's going to be along this arc, stop right there. There it is. So there you go, 2 pi thirds. Easy enough? Yeah, it's not bad. Let's do another one. Now this might throw you a little bit. So in that last problem, r was 2, right? I didn't state it because you guys stated it for me, but in that last problem, r was 2. What's r in this problem? R can be negative. I actually don't like it. I like to take the convention where r has to be positive, but a lot of books don't do that, so I put up with it here. By the time you get to Calc 3, r is never negative. So let me show you what that means. In this particular case, when r is negative, I'm going to actually do the angle first. So go out an angle of pi fourths. That puts you kind of looking in this direction right here, right? But then instead of going out 1 to here, that's what it would. This would be the point if it were positive 1 comma pi fourths, right? But what do you think you're going to do then? Instead of going out in this direction, go the other way, and here it is. So negative 1 comma pi fourths would be here. So you look in the direction of an angle of pi fourths in the first quadrant, and you go the opposite quadrant, opposite direction. In this case, a distance of 1, opposite direction. Does that make sense to you? So that's a little weird. Are these angles unique, by the way? I mean, I'm sorry, are these, well, it does break down to the angles being unique, partly at least. Are these points unique? Are the representations of these points unique would be a better way to say it. The points are unique, but at least for any particular coordinate system. But are there other ways to represent them?
Yes.
Yeah, certainly. So for like, for this point, negative 1 pi over 4, how could you represent it using maybe positive 1? How would that change the angle? Well, it couldn't be 3 pi over 4, because that would be, if you think about it, that would be an angle in the second quadrant, right? And we need an angle in the third quadrant, that's where this point is, whose reference angle is pi over 4. So if you went 180 plus pi over 4, or I'm sorry, we're kind of mixing units here, aren't we? So yeah, but since we're in radians, let's stay in radians. Let's go pi plus pi fourths, right? Or if you were in degrees, it would be 180 plus 45, right? Which would be 225. So what would it be then? You would take pi plus pi fourths to get your angle. So what would that be? 5 pi fourths. So the point here is the representation of points in polar coordinates not unique. And that's new because if you think about rectangular coordinates, there's only one way to represent a particular point, right? Also, you could keep adding multiples of 2 pi to the angle, right? Or subtracting. And you'd end up in the same spot, wouldn't you? Okay, so representation of points not unique in polar coordinates.